Hello. So today we're gonna go with I'm gonna start a new chapter. I think we're done with the first one. Do you guys have anything you want to ask from the first chapter? Any specific, say, passing questions that you have tried? Perhaps? No? Okay, let's get started then. So we'll start by defining what oscillation means. It is a backward and forward motion between two limits. I think that much is obvious. There are two kinds of oscillation. You have free oscillation and forced oscillation. So free oscillation means you just, let's say you have a string connected to a pendulum, and then you release the pendulum and it just rotates on its own accord without the influence of, say, air resistance or something like that. Then that would be free oscillation. Upload the files on Google Classroom. Okay, sure, I can do that. And done. So a free oscillation essentially means an oscillation without the influence of an external force. Then you also have forced oscillation, which is an oscillation with the influence of an external force. For example, say you're on a swing, the swing goes backwards and forwards, but then you're standing behind the swing and you're pushing the guy on the swing with your hands. That's forced oscillation. So if you have a free oscillation, the acceleration is going to be equals to, well, the acceleration is going to be proportional to the displacement from the equilibrium. So this A is going to be the acceleration of the object. This X is going to be the displacement from the equilibrium position. And then the reason you have a negative here is because A and X are oppositely directed. For example, imagine you have a pendulum, right? And the pendulum sort of goes and starts oscillating backwards and forwards, you can see that, let's say at this particular position, the displacement is in this direction, plus x. But the acceleration is going to be this way. Because it wants to go back to its original equilibrium position. Same thing for a spring. If you have a spring, let's say initially it is like this, and then you extend it, so now it's a bit sort of extended. So the displacement is, let's say, plus x, but the acceleration is in the opposite direction. So it wants to go back up. In fact, you've actually seen something like this before back in AS. It's Hooke's law. F equals to kx. Right? F is actually ma. Actually, I forgot to put the negative. My bad. Remember Hooke's law, there must always be a negative. There, so from here you can see that A is proportional to negative x. So if you were to draw a graph of A against x, you would actually get a straight line that passes through the center. Like so. In fact, if you work this out, and then you would actually get a second order linear differential equation. If you solve that, you wouldn't learn how to solve that in A levels, only if you're doing further math. Then in the last chapter of pure math, you will learn how to solve second order differential equations. But we haven't done that yet, so, and some of you are not even taking further math, so you just have to take my word for it that if you work this out, eventually you will get A equals to negative omega squared x, where omega is the angular speed, similar to the one that we did in chapter 1 of A2. Okay, remember that omega is 2 pi over t. T is the period. So this equation is the characteristic equation of a simple harmonic motion. Well, yep, simple harmonic motion. The characteristic equation of a simple harmonic oscillation or simple harmonic motion, whichever you prefer. A simple harmonic motion or simple harmonic oscillation, essentially most things they oscillate using this model. Let's say you get a pendulum and you just release it, the oscillation would be a simple harmonic motion. As you smack the table, and then the vibrations on the table would be a simple harmonic oscillation. Basically, anything that obeys Hooke's law would obey the equation A equals negative omega squared x. Okay? And in the context of A-level physics, most things, or I could say all things, obey Hooke's law, unless they specifically say it doesn't obey Hooke's law. But I've never seen a question ask something like that yet. So you can safely assume that they obey Hooke's law whenever it comes to oscillation type questions. So the definition of a simple harmonic oscillator is a type of periodic motion where the restoring force is proportional to the displacement from a fixed point, or you can say equilibrium, and is directed towards the fixed point. Okay. So, moving on. Okay, you can actually write that down over here. Define simple harmonic motion. So you want to write this down. Is it restoring a type of periodic motion where the restoring force is proportional to the displacement from the equilibrium? Okay. So, if you have a pendulum, well, should I use a pendulum? Well, let's use a spring. Actually, it doesn't really matter. Pendulum springs, the graph would be the same. But I think for a spring, it's easier to see. So if you have a spring and you pull the spring down, the displacement would be positive. If you push the spring up, the displacement is negative, or you could put it the other way around. The point is, if you pull down the spring with a load and then you release it, it's gonna oscillate up and down, right? As it bounces up and down, you would actually get this curve here, sort of like a sinusoidal curve. Sinusoidal means sine or cos or anywhere in between, because it depends on where you start. If you start at the highest point, then it looks like this. If you start at the lowest point, then the graph would start here. Then it will look like a negative cos graph. So depends where you want to start. If you start in the middle, then it would be like a sine graph or a negative sine graph. Okay. Maybe I should just draw this out. So if you have a spring, and let's say this is the equilibrium position, so x is 0 here, and then you let go of the spring and it starts moving in this direction, which means the graph that you would get would start in the center, assuming this is a displacement time graph, and you would go down, right? So you would go down and then go up and so on. So you would actually get like a S is equals to negative sine, some constant, well, negative sine, and then some function of t. I'm gonna call the displacement x instead, like this. However, if you start like that, actually no. Let's say you push the load so it starts at the top. So let's say this is some positive value, so maybe +2, and then you let it drop down, okay? Which means your graph would start somewhere up here. So this is actually like a cos graph. So depending on the starting conditions, you would get either a sine or a cos, or somewhere in between. Okay? So, what exactly is this function of t? If you try to work it out using the... How should I explain this? Basically, whatever's inside your sinusoidal function has to be unitless. So since time is in seconds, you need something that's divided by time. Well, there's actually a more elegant explanation for this, but it involves the derivation from scratch. You have to start from f equals kx and then go to the second order differential equation. I think I have it here somewhere. Yep, it's over here. So if you look at page 1, it's not there. Eventually, you go down here and you have to use the Moberrys Theorem, which is something that you'll learn in the complex number chapter in further math. Eventually, you'll get this guy here. But you don't need to know that. It's not in your syllabus. So instead, I'll just tell you that the function of t is actually something like this. Sine omega t. This one is actually cos omega t, where omega is your angular speed. Okay, so depending on the starting conditions, you would get sine, cos, or anywhere in between. Now, let's say we start with this one. Let's say our initial condition is actually cos omega t. So we start by pushing it to the top, and then we release it, and then it drops. Okay, so, well, technically the amplitude is a 2, so we should put a 2 over here. But let's say we do it for the general case, and we say the amplitude is x0, where x0 is the maximum number of x. So we'll call this x equals x0 cos omega t. So if I want you to find the velocity of this function, right, the velocity, and you have the displacement function, remember back in math, if you want to go from displacement to velocity to acceleration, what should you do? You differentiate with respect to time. So you're actually doing the same thing here. We start by differentiating this with respect to time. You're going to get v. This one is going to be x0. What happens when you differentiate cos? You will get negative sine omega t, and the omega is a constant, so you should put an omega out there, like so. So I know some of you have maybe forgotten this, but let me just remind you what happens when you have, let's say, when you have a function. Hang on, let me do it like this. Let's say you want to differentiate cos, and then there's some function of x, okay? What happens is you will get negative sine, and then the same function is there, and this whole thing you have to multiply by the derivative of the function. Similarly, if you differentiate sine of x, you would actually get cos of x times the derivative of the function fx. So that's how you get this. V is equals to negative omega x0 sine omega t, which means if your displacement function is a cos, your velocity function would be a sine. So if I were to draw the velocity function right here, what are we going to get? We should get a sine function. Okay, so if I combine these two graphs together, let me draw it together right here. So let's say x0 is rate. Blue is oh no, sorry, this should be x. Blue is velocity. Blue would be negative sine, so something like this. So as you can see, when your displacement is 0, when it's at the equilibrium, my velocity is a maximum value. Similarly, when my velocity is 0 over here, so v is 0, my displacement is some maximum value. Which makes sense, because when something oscillates and it reaches the highest point or the lowest point, it has to stop before it can go in the other direction. So when it stops, the velocity should be 0. So you see when your displacement is some maximum value, or over here, the velocity is always going to be 0. Okay. Now, how do I find the acceleration then? Well, to find the acceleration, we differentiate this again. We're gonna get negative omega squared x naught cos omega t. So if you look really carefully, you'll see that I can actually write it like this. Hang on. See this guy here? This guy is actually x from the original expression that we got earlier, which means we can actually write this as negative omega squared x, and that's how we get this in the first place. There we go. Okay, so that's simple harmonic motion. Okay, right. What next? Oh yeah, something important. If you look at the first equation, and I ask you to tell me what the maximum displacement is, aka the amplitude, you can immediately look at the equation and tell me the answer is x naught, right? Because this guy is going to be the maximum, the amplitude. You've learned this in math. What if I show you the velocity equation and I ask you to find the maximum velocity? What is it going to be? Well, the way you think about that is by looking at this part here. Okay, you see sine omega t is actually going to be anywhere, the range for sine omega t is anywhere between 1 and -1. Which means if you want v to be some maximum value, sine omega t should be either -1 or 1. Okay, so for v to be equals to the maximum value, sine omega t is equals to ±1, which means your maximum v or your v naught would be equals to omega x naught. There. What about my maximum acceleration? Well, you just have to look at this guy right here. You see that the only variable is x, right? X is the variable, the thing that changes. So the maximum value of x is x naught. Therefore, my maximum acceleration is just omega squared x naught. There. Okay, so basically these are the couple of things that you gotta know. And then we're done. Okay, so let me just walk you through what to write for this one. So for part 3, right, starting with 2, derive an expression for the velocity v. So 2 is this one. So instead of using this one here, let me just make some slight modification. So instead of starting with 2, let's say start with x equals to x naught sine omega t. So that means v would be omega x naught cos omega t. And then part B, derive an expression for the acceleration. So you just differentiate this with respect to time again. And you see that this guy here is actually just x. And therefore you get a equals negative omega squared x. Okay. So, part C, compare 3b to equation 1, obtain an expression for angular velocity in terms of the spring constant and mass m of the oscillator. Then using the definition of angular velocity, obtain an expression for the period t. Alright. So for this one, what's equation 1 here? Okay, so equation 1 is just from Hooke's law. A equals to negative k over mx. Right, so you start with Hooke's law. F equals to negative kx. Ma equals to negative kx. So A equals to negative k over mx. A here is going to be omega, negative omega squared x. Cancel the x, cancel the negatives. Omega is actually 2 pi over t. Which means my period is 2 pi squared m over k. So t is actually 2 pi square root of m over k. And there we go. So this particular expression is quite useful when you are looking at waves in a string. Remember? Oh, we never actually did that, did we? Waves on the string. Did I show you guys the waves on the string thing? Oh no, we didn't. I think we just did that. Oh yeah, we did, yeah. We did the waves online with the January students, but for you guys, I think I managed to show you how the first harmonic, second harmonic, third harmonic looks like, right, on the string. Well, those of you who are doing physics anyways. If you remember back when we did stationary waves, you get this string, these vibrating strings. And to find the period of the strings, you can actually use this equation, because the strings are actually oscillating in simple harmonic motion, where m is the mass of the string itself, and then t is the period of the waves on the string, k is the spring constant of the string. Anyway, this one is just like some extra stuff. Oh wait, everyone's doing physics here. What am I saying? For some reason I was thinking I was doing math. Never mind. Ignore me. Okay, so right. So if you look at the not here. If you look at the graphs for displacement, velocity, and acceleration, you'll notice that displacement and velocity has a phase difference of pi over 2. Similarly, for velocity and acceleration, there's a displacement of another pi over 2. And the phase difference between displacement and acceleration has a phase difference of pi. Right? So, you look at this and let's say, what is the phase difference between velocity and displacement? So the answer is plus minus pi over 2. Acceleration and displacement, plus minus pi. Velocity and acceleration, plus minus pi over 2. There we go. Though in the context of A-level physics, typically phase difference is expressed as a positive value rather than a negative value. Right. Next, determine the maximum displacement possible for a body undergoing simple harmonic motion. What's equation 2 again? Oh, this one? Okay, so if you base it on equation 2, let me write it down here. So this extra term here is actually the phase displacement term. So you can move the graph in either the left or right direction. But in A-level physics, we don't usually include the phase displacement term, so we just ignore that. So usually it kind of looks like this, which means the amplitude is just r. Okay, similar to what we were just doing earlier. Now next, we're going to show that the velocity is equals to plus minus the angular speed and then this thing. We want to prove this expression. So this expression is very useful because sometimes they don't give you the time. They've only given you the angular speed. So you need to use this to work out whatever it is that you want to work out. So how do we show this expression? Let's say we have x equals to r sine omega t, which means v must be r omega cos omega t, right? So x squared plus v squared is equals to r squared sine squared omega t plus r squared omega squared cos squared omega t, and then wait a minute.
탕수육이요.
Wait, I think I've messed up something. Whoopsie daisy. Get rid of all that. How do I prove this again? Let me think. Hey Danny, hello. Trying to think how to prove this. How do I go about doing this again? Oh, I get it. So we know that the maximum amplitude is, the maximum displacement is r, so we can actually put that into this guy, which will give us x naught omega cos omega t, right? And then no, that's a bit messy. What's the best way of doing this again? Suddenly I'm drawing a blank. Oh no. Oh, I get it. Right, we have to square both sides. Okay, so from here we square both sides, we get x naught squared omega squared cos squared omega t. Okay, and then omega squared, and then here we have x naught squared. I'm just rearranging this. X naught squared, and then cos squared omega t, you can actually write it as 1 minus sine squared omega t. And we know what sine squared omega t is actually this guy here. Right, so from here we can actually write x over r equals to sine omega t. So x over x naught is equals to sine omega t, which means sine squared omega t is x squared over x naught squared. So we're going to take that and chuck that in here, which means we're going to get 1 minus x squared over x naught squared. Multiplying this guy in, we get x naught squared minus x squared. Square rooting both sides, we get plus minus omega. X naught squared minus x squared. And there we go. Ta-da! Yep, there it is. So this expression is very useful. It would do you well to remember this. Or well, know how to derive this. Okay. You guys good? 5, 4, 3, 2, 1. Okay, moving on. So, next up we'll sketch the variation of the displacement x with respect to time. So suppose we have y equals to x equals to x naught sine omega t. That means the amplitude will be x naught and you just get a sine curve. And then for velocity, imagine you differentiate this, you get this guy here. So again, the maximum is x naught and negative x naught. Well, I'm just repeating myself at this point, aren't I? So this would just give you something like that. And acceleration, you differentiate this guy, you get negative omega squared x naught cos, well no, not cos, sine omega t. So you're plotting a negative sine graph. Oh wait, this is actually omega x naught, omega x naught, omega squared x naught, omega squared x naught. So this would be a negative sine graph, which means it should look something like this. Notice that the amplitudes are not just x naught. X naught is the amplitude, which refers to the maximum displacement, but the maximum velocity is actually omega x naught. And the maximum acceleration is omega squared x naught. Okay, so just take note of these things. Okay, next up we'll look at the kinetic energy of the body in terms of x, the displacement. So we know what kinetic energy is half mv squared. And we also know that v is equals to plus minus omega square root of x naught squared minus x squared, right? So we can take that, chuck that into this, and we get half m omega squared x naught squared minus x squared. If you expand this guy, you would get this. Hey, I forgot the omega. There we go. Notice that this is actually a constant because x naught is the amplitude. And notice that these terms here, they're all constants as well. So the only variable is this little x here at the end, which means you're essentially plotting a quadratic. In fact, this is a negative quadratic because the coefficient of x squared is a negative, right? So if you draw a graph of the kinetic energy against the displacement, you should actually plot a negative quadratic with an interception point at half m omega squared x naught squared. Because imagine if your displacement is 0, then my kinetic energy is going to be some maximum value, which is this guy here. Okay, it's just to make sense of what this means. The oscillating spring is actually fastest when it's at the equilibrium position, and the velocity is 0 when it's at the extremities, at the highest or lowest point, because that's the point where it changes direction, right? So naturally, the velocities has to be 0 at those points and maximum in the center, which makes sense because if you look at the kinetic energy equation, when x is 0, my kinetic energy is some maximum value. When x is non-zero, I would subtract this by some amount and therefore it decreases. And when you're at the maximum point or the minimum point, that's when your x is equals to x naught or negative x naught. Doesn't matter because you're squaring it anyways. So this one minus this one would become 0. So at the highest or lowest point, the kinetic energy would be 0, which means it's not going to have any velocity. So far, this all makes sense. So if you sketch this, it actually looks like a negative quadratic. Kind of looks like that with some maximum point of 1 over 2 m omega squared x naught squared. So we're done with kinetic energy. How about your potential energy? Well, the potential energy of the body is actually going to be, you've actually done this before in AS when we did Hooke's law, deformation of solids. For anything that obeys Hooke's law, what is the potential energy? It's half kx squared, right? So what does half kx squared look like when you plot it on a graph? Potential energy, displacement from the center. This is a positive quadratic and it should go through the origin. So it kind of looks like this. Okay, so when your x is 0, that means it is not extended. the elastic potential energy should also be 0 because you're not extending it. But when you extend it, the elastic potential energy increases to some maximum amount when your x is x0. Now, what happens when we combine EK and EP together? Okay, if you remember the conservation of energy, the total energy of a system is actually the sum of the kinetic energy of the system and the sum of the potential energy of the system. And according to conservation of energy, the change in total energy must be 0, which means they should add up to give you the total energy. Let me just show you what that looks like here on the graph. There. So the orange line represents your kinetic energy, purple line represents your potential energy. When you combine them together, you get the black line over here using the principle of superposition. Right, if you combine this with this, you get this. There you go. Okay. Next up, we're going to look at the idea of a resonance. So what is resonance? Resonance is what happens when an external force with a frequency equal to the oscillator's natural frequency is applied to the oscillator. Its amplitude would increase dramatically. So you can actually write that down somewhere here. By the way, you can sketch this right here. EK and then EP. And then resonance, the definition is right there. So I'll leave this here for you to write down. I'll give you a minute. Okay, all good? Now let me explain what resonance is. Suppose you're on a swing, right? And then you're on a swing and it goes backwards and forwards. And then you have your friend behind you that's pushing the swing. Whenever it comes to him, he pushes the swing. Comes to him again, pushes it. So he's pushing at the same frequency as the swing's natural frequency. So what happens when you do that? The swing's amplitude gets bigger and bigger and bigger, right? So whenever you apply a force with the same frequency as the object's natural frequency, it's going to amplify the motion and it's going to sort of increase the amplitude. However, if you apply the force with a frequency that is half of the natural frequency, you would actually dampen the oscillation. Another instance of resonance is, you know, when you have like a wine glass and you sort of move your thumb over the wine glass, the wine glass sort of starts to sing a little. And if you look really closely, you see that the wine glass is actually sort of oscillating. It's very subtle, but you see the wine glass sort of go like this. And the reason that's happening is because if you rub along the rim of the wine glass with a certain frequency, you would induce resonance in the wine glass. Similarly, you might have experienced this before. Let's say you have a subwoofer. You know what a subwoofer is? It's not quite sure how to describe this. A subwoofer is like the bass, right? It's like this box that you would use. It's like a musical thing, an audio subsystem. So if you have a subwoofer installed, you would feel the bass, and feel the sort of like the boom 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 kind of thing. And sometimes you might notice that your furniture would start to vibrate when that happens, or maybe your ceiling would start to shake quite a bit. And that's because resonance is happening, because the natural frequency of the ceiling is equals to the frequency of the subwoofer. So things like that. Resonance is typically not a good thing to have, because it would induce unwanted vibrations in a system, which would potentially compromise the system itself. And an example, or rather extreme example of this, is the Tacoma Bridge incident. I think I have it here somewhere. Oh wait, I think I've shown you guys before, right? Not sure whether I've shown this to you before. This one. So this is due to the, if I'm not mistaken, is due to the wind. So the wind coming in and the wind going out sort of generates this. It comes in and comes out with a particular frequency, which generates a resonance effect, and it causes the entire bridge to start to vibrate. And because this is a resonance, the vibration keeps building up. In the TV series Flash, Flash can vibrate at the same frequency as another object and go through the object. Is that realistically possible? Well, in order to go through another object, technically by going through an object, you are diffracting through an object. So your wavelength has to be smaller than the wavelength of the other object. Just because you have the same frequency, I don't think you would be able to pass through an object. I think that's just science fiction. That is what I know. So, well, that is what I know so far. I might be wrong, because I'm not an expert in the field, but from what I know, I don't think that's possible. Yeah. Anyway, as you can see, resonance can be a very devastating phenomenon. In fact, usually we don't want resonance, but sometimes resonance can also be useful because microwaves use resonance to heat up water molecules in food, right? So how a microwave works is it induces. So microwave has the same natural frequency as water molecules. So when you blast water molecules with microwaves, the water molecules would start to vibrate and the amplitude increases. And later on in A2, you will find that you will learn that the temperature of an object is directly proportional to the kinetic energy of the object. So as the amplitude increases, the kinetic energy would also increase, and then the temperature goes up. And for musical instruments, a resonance is also very useful because it amplifies the volume of something that you're playing, for example, in a guitar or a violin. And also things like X-rays. This one we'll do much later in medical imaging. Wait. Oh yeah, it's still there. They took out some other stuff, but X-rays is still there. And also shortwave walkie-talkies uses resonance as well. However, like I said, it could also be devastating, like the Tacoma Bridge incident or earthquakes, right? So how do you reduce resonance? You need to damp. You need to introduce damping. So damping essentially means loss of energy from the system due to a continuous force opposing the motion. For example, say you are swinging on the swing and someone pushes you in the opposite direction. It's kind of like friction, right? So if you're swinging this way, your friend pushes you this way. If you're swinging that way, he pushes you that way. So if that keeps happening, eventually you would come to a stop. So that's what damping essentially is. So, there are three kinds of damping. You have light damping, where the amplitude of the object decreases exponentially, right? Because you can see the amplitude goes down slowly over time. If you join the extremities of the amplitude, you would actually get like a exponential graph. So that's why I said the amplitude decreases exponentially. So technically, since it's decreasing exponentially, it would never reach zero. So even when something that was previously vibrating has stopped, it hasn't actually completely stopped. It's just vibrating in such a small magnitude that you can't discern with the human eye. So there you go. We have light damping. We also have heavy damping. Do I have heavy damping? Yeah. Heavy damping. So heavy damping kind of looks like this black line here, where it never completes a single cycle. So it just goes on like this and just stops. But light damping completes several cycles before it comes to a stop with air quotes, because it never technically stops. Critical damping means heavy damping, but it stops in the slowest, in the fastest amount, how should I say this, in the shortest amount of time possible. So there are different curves for heavy damping depending on the amount of damping that you introduce to the system. But if you can introduce, how should I say this, if it damps with the shortest time, that is considered critical damping. Essentially, that's it. Okay, so where is it? Over here. There. So you can draw that here. Critical damping means it just drops like that. And then under damping or light damping means it sort of drops like this, and it completes multiple loops. But notice that the period of the oscillation doesn't change, only the amplitude changes. And then for overdamping, it's sort of goes down like this. Well, it goes like this and like this. Takes a lot longer than critical damping. Essentially, it's like a longer version of critical damping. Okay, so in what cases do we use damping? Hey yo, Elise, hello. In what cases do we use damping? Car shock absorbers. So imagine you're in a car, you're driving, right? And then you go through a particularly bumpy patch of road. So if your car has no damping, that means when you bounce past the bumpy road, your car's gonna start undergoing simple harmonic motion, which means you're gonna go like this, which is of course unpleasant, right? So what if we use light damping? Well, if we put light damping, it's still going to bounce, but it's going to decrease exponentially. So it's going to go, and it sort of decreases exponentially, which again is not great. What if you have heavy damping? Then it just goes like this. Again, it's also unpleasant, right? So you want critical damping because you want it to stop bouncing in the shortest amount of time. Oh, there's also a graph that you should know. So whenever you draw the amplitude against driving frequency graph, so driving frequency refers to the frequency of the external force, right? So could be the guy that's pushing the swing, or basically anything that's the external force. So if your driving frequency matches that of the natural frequency f0, f0 is the natural frequency. So everything in nature has its own natural frequency, which depends on the material that it's made from. So my table has its own natural frequency, my ceiling has its own natural frequency, the wine glass has its own natural frequency, and so on. So if your driving frequency matches the natural frequency, the amplitude of the object would increase dramatically. So if it's undamped, you go all the way up here. Well, technically, if it's undamped in an ideal situation, the peak would actually be infinite, and it would be completely sharp. It's like a pointy peak, and it stretches all the way to infinity. Obviously, that's not realistic. You don't actually get something like that in real life, but you used to put shock absorbers in your skate shoes to absorb the shock from the big jump tricks. Ah, yeah, there we go, yeah. That's another way you could use damping. True. Yeah, so damping has its uses. It's not, I mean, unless it's unwanted, but usually damping is pretty useful. If you have heavy damping, you can see the peak gets dropped all the way here. If it's heavy damping, it drops even further. Okay, so that's essentially what the graph looks like. This is just something you have to know because they might ask you to draw it in the exam. Okay, so we are done with simple harmonic motion. So all that's left is to go through the questions, which there is a significant amount of questions. I think we'll do that tomorrow. So before we end for today, let me just briefly go through everything that we know so far. Okay? So let me just move that here. So we know that for a simple harmonic motion, the acceleration is proportional to the displacement from equilibrium, and this is the characteristic equation for simple harmonic motion. And we also know that the maximum velocity is actually, or well, maximum speed is going to be omega x naught. And the maximum acceleration is omega squared x naught. And you should also know that the velocity is related to the displacement with this via this equation, like that. And then what else do we know? What else do we do? Anything else? What other equations do we have? Oh yeah, there's also the kinetic energy. Kinetic energy is half m omega squared x naught squared minus x squared. And then the potential energy is half kx squared. And the total energy is kinetic energy plus potential energy. And then we also did resonance. So you have to look up the definition, sort of refresh memory. And then what else do we have? We did resonance, and then we did damping, right? We did damping. There are 3 kinds of damping: light, heavy, and critical. And then when you draw the graph of the amplitude of the object, the oscillating object, and the driving frequency, you will get a peak at the natural frequency. Essentially, that's it. Oh, we're done. Finito. Okay, so tomorrow we will, tomorrow and the following class, we're gonna try to finish all the questions on oscillations, and then next week we'll start with a new chapter. Okay, so we shall stop here for today, I think. Wait, let me think. Let me see, how many questions do we have? Zoom out, zoom out, zoom out. There's actually not that many questions, so we might actually be able to finish this next class. Okay, so I hope you guys have been working on your working on the past years for gravitational fields. If you haven't, I highly recommend that you start and ask me if you're stuck. Some of you have started already, which is great, but most of you haven't, I think, because I haven't gotten any questions. Alright, Danny, catch you later. Bye-bye. Thanks for dropping by. Okay, so I think we shall stop here for today. Right. I'll see you guys then. Bye-bye.